Muchas gracias. Bueno, bienvenidos a todos. Muchas gracias por su presencia. Esta charla...
Hello, welcome everyone. This session is part of the small farm project. The Aapresid has two types of projects: local projects that we call chakras and regional projects that we call theme networks. This presentation is based on the chakras system that was created as a result of demands of growers who get together to find concrete and sustainable solutions with a systemic view. A small farm or a chakra is made up of many players. We first have the group of growers. The group is created, then we have a technical development responsible person who leads the project, coordinates the trials, and generates information about the farm. There is also an experts table that provides support to generate information and protocols. Then we have the coordination. I am the coordinator. And the link between the players, among the players, and I focus on the quality of the data we generate with the project. All these players act together to meet the demands of growers. At Sistema Chakras, we work with two purposes. We want to learn producing because we want growers to participate in the generation of information and protagonism in network. As I've already said, there are many players who participate in the generation of information. Chakra America is in the sandy pampa in the west of Buenos Aires, close to the province of La Pampa. It's a region with slight slope and consequently deficient drainage, as a result of which soil is susceptible to flooding. So in this presentation, we will share the results of the chemical quality of the water table, and we'll learn about the importance of getting information about the water table to manage saline soil. We will listen to the presentations by three speakers coming from different countries who will share with us their vision on how to manage soils. And this a speaker from the Netherlands, Luciano Lehr, agriculture engineer. He's a technical responsible person at La Chacra. Cristian Alvarez, agricultural engineer, who has a PhD in geological sciences. Cristian works at INTA's extension agency, and he's a professor at the National University of La Pampa. Andrés Parra is a consultant at Sol Doctors Company. Hanneken Hismes is a researcher at Wageningen University. She's an expert in soils. And Dr. Kate Negash, who is a professor at Amsterdam University. Without further ado, I'll give the floor to Luciano. Hello, I am Luciano Lehr. I'm the technical responsible person working with development at Chakra America. I will make a brief introduction since Solen has already described the project. Chakra America is in the sandy pampa with a slight slope which affects the water movement on the surface. That water has to going through evapotranspiration, percolation, with the change in land use, climate change, and physical soil degradation. Over the past few years, what we have seen is that after historical flooding, agricultural surface has been lost as a result of flooding, desalinization, and this is why a group of growers, specifically eight growers or 8 companies in the south of the province of Córdoba and the west of the province of Buenos Aires and northeast of the province of La Pampa, they got together to create this small farm called Chacra America, the goal being to mitigate and recover soils with a saline water table through best agricultural practices adjusted to these environments in order to maintain or increase production capacity. First, we will talk about the water table, the dynamic, the behavior of that water table, and the chemical quality in 2 periods. And we will see how it affects the production and the physical structure of our soil. Here, what you're seeing is the monthly variation of the water table. You can see the behavior in the depth of that table going from plus 70 to minus 70 centimeters. And the behavior shows that there is a period, a loading and a downloading period. The loading period happens when the water table is close to the soil surface, and this usually happens in autumn and springtime. And the time when there is a reduction in that water table, that is, when the water table is further away from the surface, this happens in summer. During these 2 years, 2022 and 2024, well, samples from that water table were taken in July and in August. It was a loading period. So the question we asked was, what happens with the quality, with the chemical quality of that table when it's closer to the surface as compared to the summertime when there is a reduction in that water table, or in other words, when the water table is further away from the surface. Samples were taken in 2024, in January and in December. In order to add value to that graph, we should see that there is a difference between winter in 2022, when the water table was closer to the surface, and on average it was 1 meter 80 centimeters away from the surface. On the other hand, we see that in summertime, in 2024, that water table was further away from the surface. That is, those data showed around 2.7, 2.8 meters. On the other hand, especially because of the different environments, we were able to see that the saline soil was at 1.8 meters, and the agricultural cycles were placed at 2.7, 2.80. Now, getting into the quality of that water table, and the first variable that we analyze is electrical conductance. In 2024, 39 sites were analyzed, and they were classified based on desalinization risk, which was based on certain thresholds. Less than 0.75, according to the literature. This allows for normal germination and growth of crops. And on the other hand, there were 35 sites that were above that 0.75 and that were affecting projection and physical structure of the soil. Around 90% of the samples. Now, when we started talking about conductivity and when we started to compare that based on the different periods, let's remember that we had a loading period when samples were taken in 2022 as compared to a water table rejection period, and the samples were taken this year in 2024. And we did not see significant differences in terms of conductivity. But we started to analyze the environments, and we saw that regardless of the period, we could see that the low ones showed an increased conductivity on average. And we saw there was a large variation, and in turn there were also extreme values. And this was due to the chemical composition of those salts, which are more soluble salts that are dragged by water from higher to lower areas. And on the other hand, we saw that the average value on the slopey areas were on the hill prairies were what we see on the screen. There are agricultural cycles where the conductivity average was 0.4 decimeters per meter. So when we analyzed an additional variable such as pH, we found that a pH of 7.5 showed a higher frequency in pH values. We also saw that that data were scattered in terms of the hilly area, and we also saw that with the same pH value, conductivity was quite variable. This was due to the composition of those salts. So the question we asked is, why is it so important to take conductivity into account in those water tables? And what we saw is that in semi-slopey areas, conductivity was 4.4. And if you take a look at the graph or at the chart, the blue box, the crops that are most widely planted in that area, like corn and soybean, are below in terms of conductivity values than what we found in that water table. So if that water table represents a loading at some point in time during the year, this might affect projection, and not only projection, but also the physical structure of that soil. When we analyzed pH that was above 7.5, and in turn, as we all know, this restricts the availability of some nutrients which are important for crops. When we when we send the samples for chemical analysis, not only do we request salts concentration, but also the composition of those salts. We want to know total cations and anions because this helps us determine two indicators, such as residual sodium carbonate, and the sodium absorption ratio. And these indicators show the risk of increased sodium and alkaline content in that water table. On the y-axis, you can see both indicators in microequivalents per liter as function of the accumulated frequency percentage, and two threshold values depending on the indicator. In the case of residual sodium carbonate, is 1.5 milliequivalents per liter. In 2024, we saw that 74% of the samples were above this threshold. On the other hand, in terms of RAS, we used a threshold value of 15 milliequivalents per liter, and in 2024, we found over 50% of the samples in that level. Now, in terms of the trends for 2022 and 2024, we did not find any significant differences among the data in those two periods. But in other words, what these indicators are showing us is that sodium may stay on the surface, and the problem it may cause in the structure or in the physical health of the structure is the dispersion of colloids, degradation of the soil physical health in terms of structure, porosity, infiltration. But we did not stop there. We wanted to see how those water tables within our small farm could be classified. And we found the following. In terms of anions, there was a larger concentration of bicarbonated water at the bottom right, and that anion came together with the sodium cation, which is on this side, and the classification was sodic bicarbonated type. The chemical characteristic of these salts is its solubility, and depending on this, the salts or the water may be a problem or not. In terms of sodic chlorated water, it's a temporary problem. Those salts can be washed out more easily, and on the other hand, the bicarbonated salts are more soluble, so the problems are severe and permanent. Where did we find those salts? In agricultural sites with slope and semi-slope. So what we learned from this is that we have to go back to the question we asked initially at the beginning of this research. What happens with those two periods where the water table dynamics was that it was further away from a surface at some point in time and closer at a different point in time? We did not see any significant differences in terms of quality, because we can say that the water table can be an opportunity or a threat. In the case of our small farm, we thought it was a threat because of the salinization risk. So if that water table gets to the surface, we may not only lose our production, but also affect the soil chemical health. So one of the recommendations, and Cristian will come back to this, is cover throughout the whole year to cover our plots. On the other hand, we also focused on the soil. We had soil analysis carried out in 2020. This is still a line of work that is ongoing. What we did in this case was to analyze conductivity as one of the variables, and we tried to see what happened during those 4 years of transit at the farm. This is a map that helped us understand the processes. This map shows the hydrate risk. Every establishment at this small farm has its own water level. It has drainage, pathways, depression, so we wanted to analyze every variable to see what they meant. Here you will see the 5 lots. We worked in the same establishment because of time constraints. We used conductivity in 2020, conductivity in 2024, and we did find some differences. In terms of conductivity differences, we saw that in some points there was a 10 points decrease. This means that there was a good improvement in terms of reduced conductivity. Then there were other times when those points were the green ones or the yellow ones. Conductivity, in other parts, conductivity had dropped very little, maybe less than 10 points. And in other areas, the levels remained constant. So we had to characterize every number and see why conductivity had decreased so much in one area and so little in another area. So on this map, we were able to see that those areas where there was a very big difference, for example, 54.8, were those points that were at the higher level, where the plot was higher, and they were not so much influenced by the water table, unlike what happened with the other areas that were down the slope and were more affected by that water table with a higher hydrate risk. So when we got together to discuss this with growers, and when we showed this analysis, the grower told us that in these areas, they get 10, 15, or 20 hectares with this type of crop, and they see an evolution here. On the other hand, there were some areas where the difference in conductivity was not quite significant, but according to the pictures, we had pictures from 2020, and we also have the coordinates, so we go and visit the same area, we take pictures, and then we compare. And we saw that depending on the aspect, these are areas where what growers do is close one area, use the roller, use a roll, and depending on the cover crop, this generates more light, reseeding or replanting of these species, trying to generate cover. What type of cover? Any.
Imagen del 2020.
What we see in this picture from 2020 and 2024 are processes. In 2024, we have the cover, we have evapotranspiration that was changed with evaporation. When we have evaporation, the salt remains on the surface, resulting from the capillary ascension. And so the infiltration occurs and that water table goes down. As a conclusion, and our learnings, when we tell the farmer that in all these environments, or in most of the environment's conductivity went down, in higher areas, we need to continue with that coverage. We need to continue with the evaporation process, try to depress that water table and not to go back. And also, we know that we are influenced by rainfall.
Bueno, les tenía que leer.
I had to give some announcements, but I will leave that for later. I will just, good afternoon, thank you for coming. Thank you for being interested in a topic that for me has been one of the main causes of important agronomic losses. If we thought this or thought about this 10 years ago, it didn't generate so much interest. This was a topic that had to do with some environments that we had in flood situations after 1986. But I think that something happened, something different happened in these systems, mainly associated to simulations. What Lucio was talking about today, that those cyclic environments that we had were floods of 2015, and 2016 left their consequence. We have an impacted surface that is threefold the surface that we had in the past. We made survey of areas covered with salts. They were only about 45 and 6% in the area. I'm talking about the western Buenos Aires, southern Córdoba, and eastern Pampa, La Pampa. After 2016, the impacted area was about 26% of the surface area. 26% of the surface area, which means that there are farmers that had 80% of the surface impacted by flooding, and others that didn't have that same impact. In order to continue from what Lucio was saying regarding the soil analysis in this part of the farm and relating this to the water table, I wanted to share with you some things that are starting to be expressed in the soil. Those salts, he classified them through a keeper triangle. You can say something about this, but we just wanted to show that, okay, we know our salts. We have an arsodol, an aplustol, an aquastol, you name it, with a name. We also wanted to give a name to the water table that's really influence us. There's some things that start to happen to us. He said that there are water tables with salts which are not much soluble, or salts that are very soluble. And I want to introduce you these water tables, very soluble water tables to the left and less soluble to the right. What does that mean? I relate this to severe impact on the productive quality of environments. Why we describe this way? Because these are water tables that have misnamed acids, carbonates. And that causes a change in the soil pH, mainly associated with one of the main strategies, which is nutrition. So it reduces the capacity of many nutrients. These carbonated salts in the soil profile do not only impact on those nutrients availability, but they also condition us physically. There are two conditioning physical properties for carbonates. When they dry, they become very hard. The resistance results in compacted and compressed roots. When the environments and semi-hills start to be spotted, those salts are impacting on us. Not only when the environment receives less water, but also when the environment receives a lot of water, because another impact that they have is as water wants to getting those carbonates that are salts, where are they going to grow or to develop? Inside the soil, in the porosity. Therefore, we have smaller pores, and with this, the infiltration is less. So, with the same water regimes, we have flooding periods, and therefore this causes crop loss. That's why he referred to the water risk maps. We try to work with variables associated to this that is so controversial. In electrical conductivity, we have many species to incorporate in our systems, but we don't have any species that prevent frequent or periodic floodings. So oftentimes, monitoring things so that we can understand how frequent those floodings are. They are withholding time, or they are holding time, and how long they persist. Let us identify different variables, especially those that have to do with electrical conductivity and pH. Another important variable is that if we say that carbonates are impacting on the movement of water, they are also conditioning the immobility of many of the solutes that we put in the surface. Many of these environments carry problems associated to the stacking resulting from the fact that we don't extract the sprayer when we work on the plot. So the stacks linger on in time, and so we end up having phytotoxicity effect. This happens frequently, and sometimes we find it difficult to identify this, and this has to do with the salts. We can see the salts here in dark or white colors, and they make us aware of the presence of carbonate, which is a very little soluble water. As Luciano was presenting, this farm has data related to phreatic level meters or water table meters. That recharge capacity gave us different flooding frequencies. What we have been understanding is that water tables don't have the height as a function of texture, but rather as a function of the salts present in the profile. Those salts present in the profile become the scenarios that we try to describe. There are water table and sandy salts as ours. They go up to 60 or 60 centimeters, and in 2 kilometers away you have the ascension of water tables of as much as 2 meters or 1.5 meter. In these scenarios, we don't only consider different planting dates, especially regarding cover crops, combining legumes and grass crops, but also this is related to when that cover crop becomes dry. Sometimes we are planting those crops in green on green. What we want to see is that you can't believe that water tables go up at the same time always, but in these pictures to the right, you can see that water tables are not only a function of texture and salts, but also it's related to the frequency they come up or they go further up. So we need to understand not only the depth of the water table, but also the pulse dynamics. The intrinsic quality of that water table will give us information about the productive capacity of those environments and the potential loss that we might find as depending on whether the water balance is positive or negative, depending on the production cycles that we are generating in this kind of scenario, especially with the water rhythm or the water pace in these semi-hill areas. This is what we wanted to share with you in La Chacra. We are trying hard to understand, classify, and check each of these environments. Which of their characteristics are related to the water pace? Some environments in the farm that are having their sixth crop, but there are also other areas that are having only their first crop. The grower, the farmer, is anxious to recover those scenarios. And the most limiting situation is when we have water tables that are nearby and their characteristics are associated with salts. And when determinant to the quality and the frequency of these water tables coming up to the surface, this allows us to analyze the different rates. So thank you very much for listening to my presentation. I'll be glad to answer questions. Good afternoon. I'm Andrés Parras. I wanted to thank the Embassy of the Netherlands in Argentina. I want to thank Aapresid and also Luciano and Cristian for including me in this panel. I'm coming along with Hanneken Hesmans in Kate Negas. We were commissioned with a work of exchanging knowledge and experience and compare our own experience with the situation in Argentina. What we want to respond is sharing with you the problems that we are facing in the Netherlands, in Europe, regarding salinity, and to share this with Argentina and what we get from Argentina, how each country is learning from the different situations faced, and how can we deal with salinity. Our focus points in this mission is governance landscape for salinity management, technical solutions for soil. They are very interesting experiences. We will try to conduct research to make some demonstration in the future in R&D centers that are being created in America. It's AgroInnov. We have been for some days now here. This has been a very hectic week in the farms. We've been down to America in the farm where our colleagues are working. This has been really very rich, and we have seen the problem of salinity. In spite of having differences in our productive system, the problem is there, and there are solutions that can be combined to continue being productive in spite of salinity. I work with a company called the Soil Doctor. It's a Dutch company. We have been working for more than 15 years, working in research and development, implementing projects in different areas around the world. And what we generally do is we go to the field, we make a salinity analysis, and then we work on our findings in order to improve yield. The saline agriculture, I don't know if you are using that word here. It's one more a branch of agriculture. We need to consider the crops which are more or less tolerant to salinity. Then we have to consider the integration between crop, soil, and water. So under salinity conditions, we have to pay more attention to this integration. So, and to have in mind all these three elements. Salinity is a growing problem. I won't take long to speak about that because you're aware of it. As a company, we had an experimental farm in Holland, in the Netherlands. We have different varieties. And I talk about variety because we know that some crops are more and others are less tolerant to salinity. But we can select the most tolerant ones. In this experimental farm, we irrigated with 7 different concentrations of water, river water. We combined fresh water with sea water. Most of the crops that we used were orchard fruits, but also used grass plants, grass crops, and legumes. And we saw how salinity increased. If we base ourselves in the literature, in the standard, this list that you can see here, there are some standards that tell us that some numbers probably come from the FAO, but they didn't consider the fact that this can increase, and so increase or being reduced, and the difference can be significant. In this chart, I show the cabbage crop which is very sensitive to salinity. We could double the yield using varieties that prove to be more tolerant. We control this through constant monitoring. Sampling is very important here. And this, the evolution of the soil will also tell us or give indications about the development of the crops. Some experiments can be conducted in the field. We try to give the solutions directly to the farmer so he can directly control how salinity is doing in his farm. We are working in several parts of the world, for instance, Kenya, Bangladesh, and Egypt. We have been working under salinity conditions. The literature says that if we had planted there, we wouldn't have had any yield, but we proved something different. Just to tell us, Charlie, for soils that have high salinity levels, and the infiltrated water or the underground water is also salty water, we can make beneficial use of this, and the results are interesting. In more saline soils, we have halophyte production. The halophytes, as for instance, crop that can be irrigated with salty water. See, the one that we have get to know, which is the Disertaron spicata. We call it pelo de chancho here.
Well, that's it as far as I'm concerned. I will give the floor to my colleagues.
It's great to be here. My name is Kate Negac and I work at the Vrije University in Amsterdam. I specialize in food governance, especially saline agriculture. So today I would like to tell you a little bit about what we are doing in Argentina and what we are doing worldwide. Salinity is a big challenge, but also a big opportunity. This is why we came to Argentina. Argentina is one of the most affected lands as it comes to soil salinization. But it's not the only one. We know that 75 countries worldwide are facing this challenge. We also know that this problem will grow in the future due to the climate change. But we also are aware of different solutions: technical solutions, economic solutions, societal solutions. And this is why we came here to talk to you, to network, and to see how we can deal with this problem together. Around the world, there are different saline environments. We have salinity in the coastal deltas, but we also have them in the semi-arid agricultural areas. And we try to map different projects, programs, initiatives, networks that focus on this problem and try to deal with it in different countries around the world. This week, we focus on what is happening in Argentina and how we can foster regional and international collaboration. Now I would like to tell you a little bit about 3 projects which focus on saline agriculture. This one, called Salad, features 4 different crops: quinoa, potato, tomato, and New Zealand spinach. They're all salt tolerant, and they're all crops that in 6 different countries have quite a good potential for agriculture. So we try to work with different levels of salinity, advise farmers, work together with different market niches, and see how we can upscale production of these 4 different crops, working together with 11 different partners. We are using practical pilots. We are also looking at economics and social adjustments. We are using different technologies and also different methods of learning and understanding the problem better. For example, virtual reality. Another project, this one focuses on networking. So here we are looking at how we can actually bring together people that work around the topic of saline agriculture and share the practice of measuring soil salinity, the practice of adjusting the plants, varieties, new technologies again. So this project, Sustain, it's open for everyone to join. Also, if you would be able to join and if you would like to join, you can exchange different ideas, questions that you would have. Finally, a practical project, one focusing on Kenya. So there we worked for a year with the farmers. We went to some places in Kenya and we gave practical trainings, including measuring affected soils, also choosing different varieties, establishing plots, checking economic possibilities, sustainable business models, and finally looking at how policy and government can actually support people dealing with salinity at their soils. These are a few examples of working with salinity, and if you have any questions or if you have any ideas that you would like to discuss, we are very much looking forward to that. And I would like to now invite my colleague Hanneke to present the last part.
Good afternoon, everybody. Thank you for inviting me here. My name is Hanneke Heesmans. I'm a soil researcher at the Wageningen University and Research. Just to give a little example of the three themes that we work on quite a lot, is we have a societal component in Wageningen Research. We work on food, fodder, bio-based materials, and me myself, I work in the environmental research on natural resources. So just to give a little context of why we are here on this mission. So salinity is a very complex problem. It is not just an issue of agriculture itself. Salinity impacts also overall biodiversity, human health in general, but also animal health. And it is estimated that around 3 hectares per minute are becoming more and more on saline conditions. This means that 170 million people risk their food security just because of these salinity issues. And it's expected that if this will continue by 2050, around 50% of all arable land will have some issue with salinity. It has a significant impact on the food system and ecosystem in the world. So just a little idea on salinity in the Netherlands. So the main issues that we have with salinity in the Netherlands is the sea level rise and seawater intrusion in the coastal areas. So this affects very much the area around the Netherlands on the coastal areas. Here you can see that it's the majority is in the north and in the southwest of the Netherlands. And these are actually regions in the Netherlands that produce a lot of crops, mainly potatoes, but also grains, sugar beets, but also, for example, onions. These are highly productive areas. So some of these adaptation measures that we take and that we measure and that we look at Wageningen University, many of them are being measured and implemented and tested at the moment. So for an example, we are working on different projects dealing with drip irrigation, with water management strategies, but we also use models to have a cost-benefit analysis, for example. Then we are also testing at the moment the effectiveness of biostimulants, and this is done more at a laboratory scale. And we do that to look at that as a way of adapt to salinity issues. But we also have a lot of projects abroad, and this is an example of a project in Bangladesh, which is a very different country than Argentina, a high dense population there. But we do notice that the impact is also extremely high there. The effect of salinity on the food system in the whole country is enormous. And this can range from changes in the quality of drink water, whether drink water is potable in general, but it can go all the way to livestock problems. At the moment in Bangladesh, people are already making changes due to the climate change, due to the salinity issues. They are already changing, for example, their crop management, or they're even going to a completely different way of farming, for example, agricultural systems. Just an example that we have abroad. If you have any questions, any remarks, or any ideas, please, you can contact us right now with questions, but also maybe later when this is finished, please come to us if you have any thoughts that you would like to share. And we would like to thank you for your presence here. Thank you.
Bueno,
Well, first of all, I'd like to thank our speakers for their very interesting presentations. We thought it was great to share the experience of La Chacra, but also experiences carried out and projects carried out in other parts of the world, such as the Netherlands. We have only a few minutes left for questions. I have a question for Luciano. In the picture, you showed those low areas where there was not so much change in electric conductivity. The question is, what were the activities performed there between 2020 and 2024? Was there any fertilization applied? Well, in those cases where there is a high flooding risk or water risk, usually farmers know that they have to live with that problem. As Cristian said, that's usually one of the first steps. That is generating cover crops through the species that prevail in those environments. And so that rainfalls will also help. In 2022 and 2023, rainfall has been scarce. This also helped. And in terms of changes and amendments, the risk there is usually low. Usually we don't do it because there is no slope for those salts to flow away. And when it rains, they usually go up again. Cristian, would you like to add anything? Thank you, Luciano. There is a question for Cristian. What is the right management in plots that are usually flooded, or whether it's ponding? Well, Luciano was talking about the hydro risk at La Chacra. Usually there we can have from 5 to over 50% of ponding. If you start characterizing these Stichleys spicata and other weeds, well, usually it's around 30–40% of flooding risk. Now, if we talk about plant cover, similar to the ones we have in southern Cordoba, there is 10 millimeters rainfall and there is already ponding. So it's, in those environments, the risk is about 80. This is why we always emphasize that we need to supplement our perspectives. We need to include the technological area aspects or tools and also the agricultural perspective, where we can see this teacher spicata only, or this stitchless spicata and others. Within these populations that are usually monophytic and that help us or allow us to do different things. If you do not have that ponding risk, what you can do is visit the field and see what happens if you close a small part. Usually you don't see anything else because you have the pressure there. So in these scenarios, rather than going out to find salt-tolerant species, you first have to be aware of how serious the problem is, what that plant cover tells us, and based on that, and considering other physical restrictions, you can start making decisions whether to carry out an intervention or not, or where to do it. As Luciano said, the farmers that are usually associated with those patches usually start working on 10, 15, 20 hectares. It's gradual advance that you see within that cover situation. Thank you. Well, we do not have any more time left to answer questions, but would like to invite you or encourage you to get closer to the speakers in case you have questions. Thank you again for being here with us, and we wish you a great Congress.